All right, determining a radical function from a graph. So a radical function that involves a stretch can be um, obtained from either a vertical stretch or horizontal stretch. Use the equation. So this is for the vertical stretch. This is for the horizontal stretch. Y equals a square root of x, or y equals b squared of x, or y equals square root of bx, to represent the image function for each type of stretch. Identify the endpoint. The endpoint represents the parameter hk, because if you remember where the endpoint starts, that's a good reference point to see what kind of stretch is applied. Method 1, compare vertical or horizontal distances to determine stretch factor. So this is graphically. So you're going to look. And method 2, substitute coordinates of a point to determine the stretch factor. This is algebraically. Okay, example 1. Given the following graph, determine two forms of the equation for the function shown. The function is a transformation of the function y equals square root of x. So first thing I'm going to do is I'm going to graph what the function would look like without the stretches. So I'm imagining without the stretches, but still with the translations applied. So 1, 1, 4, 2, 1, 2, 3, 4, 2. And then one more. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 3. I'm imagining this point right here, like this. 4, 2. And if I start with the endpoint here, I'll just pick 2 points to start with. 1, 1. If I go up 2 and right 4, I'm at my endpoint. So 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. So that's why I draw this graph like that. All right, so let me clean this up. This, folks, is y equals square root of x minus 4 plus 2. Okay, so view it as a vertical stretch. What is this point? This is 5, 3. So if we think about it in relative terms, so if I start here, I'm going up 1 unit, 1 unit, 1, 2, 3 units for the y value. So graphically, a must equal 3. We know h equals 4 and k equals 2. Now that we have our a value, we can write, also we can say there's no reflection here. The shape of the graph tells me there's no reflections applied. So y equals square root of x is transformed into, well, let's write it in terms of y equals a square root of x minus h. There's no horizontal stretch, plus k. So y equals a value of 3, square root of x, minus h is 4, plus k is 2. Okay, algebraically, what does this look like? If we start with our base function and we apply the transformations, but we don't know the stretch yet. We say y equals a times, I know it's a h value of 4 and a k value of 2. And then I'm going to pick a point, let's pick 5, 5. So for 0.55, that's 5 equals a times x, which is 5, minus 4, plus 2. And so that's 5 equals a times 1 plus 2. And that's how we got our a value of 3. So this is algebraically. Let's take a look at it as a horizontal stretch. Folks, I'm going to take a look at this point. So this is the key point on my stretch. That one, that is 10, 11, 12, 13, 5. So this is 13, 5. But I'm going to look at it in terms of relative terms. If I am going, let's do this in purple, from this line, 1 unit versus 1, 2, 3, 4, 5, 6, 7, 8, 9 units. So that tells me that there's been a horizontal stretch, right? But I'm going from the base function back to the transform function, so it's 1/9. So graphically, b equals 1/9. Oh, sorry. Sorry about that. The x value is transformed by a factor of 1/9. So a factor of 1/9, which means 1 over absolute value b equals 1/9. Therefore, my b value is 9. All right, sorry about that. Again, no reflection. And I know my h value is 4 and my k value is 2. So I can simply write my equation as y equals, this time I know I'm not counting an a value, so y equals square root of x is transformed to y equals no a value, or a value is 1, sorry, b times x minus h plus k. Let's fill everything in. Square root of b, which is 9, times x minus 4, h is 4, plus k value of 2. Algebraically, if I look at y equals square root of b times x minus h plus k, I don't know what the b value is, but I know h is 4, and I know k is 2. So I'm going to pick any point. Let's pick 8, 8. So for 0.88, that's 8 equals square root of b times 8 minus 4 plus 2. 8 equals square root of b times 4 plus 2. 8 equals 2 square root of b plus 2. Subtract 2 from both sides. That's 6 equals 2 square root of b. Divide both sides by 2. That's 3 equals square root of b. Square both sides. That's 9 equals b. And that is the same b value that you get. So that's algebraically. State the new equation of the curve reflected in each quadrant. So this is in quadrant 1. Let me do the vertical stretch version. Okay, I'll try to explain this as best I can in words and using the static graph I have, but then I'll do a Desmos to show you dynamically how this works. If I'm reflecting it into quadrant 2, and let me do both versions, or y equals square root of 9 times x minus 4 plus 2. To reflect into quadrant 2, I need to have a b value of -1. So let me do this. This one, I need a b value equal -1. So what does that look like? If I do that, though, this is going to change the translation value, right? So if I reflect this, so let me do this in blue. If I take this graph and I reflect it as it sits, it's going to look like this. But I want it in quadrant 2 here. So I need to translate it over 4 units and another 4 units. So I need to do -4, -4, -8 in all. So how does that work? I need to that's x minus 4. If I'm going -4, -4 to put it in quadrant 2, the endpoint, right? That's minus -4 plus -4, right? So minus -8 total. Okay, stick with me here. And that's going to be plus 8. So this becomes plus 8. So this all becomes plus 4. Okay. That's quadrant 2. For this one, b also needs to be -1. Well, what does that look like? Y equals -9 x minus 4 plus 2. But for the same reasons, if I adjust this, I have to adjust this if I want it in quadrant 2. So meaning I need to adjust the translation. So that needs to be, I need to go left by 8 units. So it's -8. So that's going to be a plus 4. Okay, what about quadrant 3? So I'm going to take this equation and reflect it into quadrant 3. Well, I need to reflect the entire thing. Let's do it piecemeal. If I reflect it, I need an a value equal to -1. So in quadrant 3, folks, what does that look like? Y equals, well, let's do -3. Well, here's the problem. I have this plus 2. If I reflect it, oh, it's getting kind of messy. Now it's over here. If I reflect it, it's just going to reflect it as it sits like this. I need to move it down so it's in quadrant 3. So I need to change the k value. I have to do this, right? So I need to go down 2 and then another 2. So this is going to be -2. Oops. for this one, I need a to be -1. Well, the same thing occurs here. If I have y equals -1 times -9 times x plus 4 plus 2, when a is -1, the same reflection happens, but I need it to actually be in quadrant 3, so the k value also has to shift. And the k value has to go to -2. In quadrant 4, for quadrant 4, let me make this a little bit easier. I'm going to start with my quadrant 1 version, which is y equals 3 square root of x minus 4 plus 2. And the other version, the horizontal stretch version, is y equals square root of 9 times x minus 4 plus 2. I'm going to transform this with a value of -1. So if I'm going from quadrant 1 to 4, I'm doing a reflection in the x-axis. When a equals -1, that's -3 times x minus 4 plus 2. But I need to adjust the plus 2. It needs to become a -2 to actually be in quadrant 4. Same thing here, a equals -1, y equals -1 times 9 times x minus 4 plus 2. When I reflect that, I need to change the k value to actually move it down into quadrant 4, the endpoint. Okay, so that becomes -2. This will make more sense when we look at Desmos. So, hey folks, over on Desmos, I have y equals 3 times x minus 4 plus 2. If I copy this over, I want to reflect it into quadrant 2. Well, I said to reflect into quadrant 2, if I do this, watch when I put a -1 in front here. Here's the problem we have. So let me zoom in. When I reflect it with the b value of -1, well, it reflects it with the reference point of the endpoint still being in quadrant 1. How do I make that endpoint move over to quadrant 2? That's where we had to adjust this by moving it over 4 units and then another 4 units. Okay, so a total of 8 units. And there it is. So minus -8. That's what I showed in the notes, right? So minus -8. If I simplify all that math, that's x minus 4 plus 8. That's just x plus 4. There it is. Okay. Okay, I want to take this graph and I want to reflect it into quadrant 3. I know I need to have an a value of -1. Look what happens when a is -3, right? It reflects it, not in the x-axis, because remember, our k value is 2. So what do I need to do? I need to move it down 2 and then down another 2. Minus 2, minus 2. Okay, so it's -2 overall. Well, let's look at it another way. If I put a giant set of brackets around here, and then I put a -1 in front, what do you think will happen? It will actually reflect it into the quadrant like we just did. Why does that work? If I distribute that -1 across, it's the same thing that we just did. So let's imagine that we're multiplying everything by -1. And there it is. Okay, quadrant 4, to make it easy, I'm going to reflect it from quadrant 1. So what do I need to do? It's reflecting vertically, vertical reflection, or sorry, reflection in the x-axis. So I need to have an a value of -1, but I also, for the same reasons, I need to shift this down. So let me do it in 2 steps. -2, -2. Okay, so -2 overall, or the other way to think about it, like I showed before, is if I put a set of brackets around here, and if I make the entire thing negative, that reflects the entire function about the x-axis. And then if I distribute that, well, we know what it looks like. Okay? All right. Let's do the other one, which was from the horizontal stretch point of view. Okay, so we know that's the equivalent graph. Oops, hang on a second. So this is, equation 1 is the graph with a vertical stretch. So this is vertical stretch. This one is the horizontal stretch version. So we're going to take the horizontal stretch version, and reflect it all into the various quadrants. So into quadrant 2, I know I need to reflect it across the y-axis, so I know I need a negative b value. There's a negative b value, but I know I need to adjust this by saying -4, -4. Okay, same deal. So that is the same thing as +4. I need to reflect this into the quadrant 3. So what do I need to do? I need to do a negative a value, but that doesn't move the endpoint. I need to move the endpoint -2, -2. Okay, same deal as before. If I throw a set of brackets around and I make the entire function on the right side negative, that does the same thing for me. That's the same as distributing that negative sign, the -1, multiplying through, and you have your reflection. For the last one, I'm going to start with quadrant 1's version of the graph, and I know I need to reflect that across the x-axis, so I'm going to have a value of -1, but I know I need to move it down into the quadrant 4, the endpoint. So again, -2, -2, or same thing as applying a set of brackets across. Does the same thing. If I multiply through by -1, I get the same transform graph reflected across the x-axis. Determine the equation of a radical function with endpoint at 3, -2, and passing through the point 1, 2. So let me draw a set of axes here. Three, -2, 1, 2, 3, 1, 2. And 1, 2, 1, 2. Okay, and then if I connect the dots here, I get something like that, right? And we know it continues on that way. Okay, there's the endpoint 3, -2. Determine the equation of this function viewed as a vertical stretch. Okay, remember the endpoint determines the h and the k value. So right away I know h equals 3, k equals -2. That's my endpoint. So h equals 3, k equals -2. So let's set those down right now. for the vertical stretch, I need to determine the vertical stretch factor. So vertical stretch factor. If I go from here, right? So I go 1, 2 units, and I go 1, 2, 3, 4 units. So every 2 units, I go 4 units up. So 2 units on the x-axis, 2 units horizontally, 4 units up. I'm going to think in relative terms. I know there are coordinates there, but think in relative terms. So 2 units on the x value, 2 units on the horizontal axis, and 4 units on the vertical axis. Remember, vertical stretch factor, only y values are affected. Only y values affected. So I'm taking the graphical approach. We'll do both. Okay. On the base function, y equals square root of x. I should do this first. Hang on, folks. Let me set that aside. Only y values affected. So every 2 units horizontally go up 4 units vertically. This is the key here. This is what I care about, going up. Okay? Now back to the base function. On the base function, y equals square root of x, every 2 units horizontally go up how many units? Go up y equals square root of 2. So go up every 2 units horizontally. So that means x equals 2. Go up y equals square root of 2 units. So how is it transformed? So I'll say vertical stretch is Vs. The vertical stretch is 4 divided by square root of 2. So every 4 units on the transform function, I'm going square root of 2 units on the base function. Let me rationalize that, folks. Therefore, my a value is 2 square root of 2. That's the vertical stretch factor. I know my transform function general form is y equals a times, the b value is 1, so I'm just going to leave it as x minus h plus k. My a value is 2 square root of 2 times the square root of x. H value is 3, and k value is plus negative 2 or minus 2. And that's my transform function using the graphical approach. Let's use the algebraic approach. The algebraic approach is y equals a square root of b times x minus h plus k. Let's plug in our values for point, use 0.12 on the transform function. So plug in all our values. 2 equals, I'm solving for the a value. B value is 1. We're only considering vertical stretch, so no horizontal stretch. X value is 1 minus the h value, which is 3, and minus 2. And let's solve for a. That's 4 equals a. Oh, sorry. One key thing I forgot that will make this work. Yeah, hang on. Sorry, folks. I should back up here. One very critical thing I forgot here is important. B value equals -1. That's one thing I forgot. Sorry about that. B value is -1. That's very important. How do I know it's -1, folks? Because which way is this pointing? It's pointing to the left. If it's pointing to the left from our base function, remember our base function starts here. If it points this way, that means there's been a reflection about the y-axis. Okay, so I forgot about that here. And that should have been a given in the beginning. B equals -1, reflection. So when I apply the b equals -1, that's y equals 2 square root of 2 times the square root of -1 times x minus 3 minus 2. And there is our final function here. Sorry about that. Okay, now on to algebraic approach. I start with my general form of the transform function, y equals a times b x minus h plus k. Let's use point 0.12. So let's plug everything in. So 2 equals, I'm solving for the a value. My b value is -1, x is 1, minus h, which is 3, minus 2, which is k. Let's solve for a. That's 4 equals a. That's -1 times -2. That's +2. A equals 4 divided by square root of 2. And we already know from rationalizing that is 2 square root of 2. So the final form of my equation is y equals 2 square root of 2 times b, which is -1, x minus 3 minus 2. So same. Algebraic approach, graphical approach. Let's do the viewed as a horizontal stretch. This one I'll throw in. A value is 1. I've not done any kind of reflection across the x-axis. So let's think about our horizontal stretch factor. And then let's work backwards to find our b value. Remember, for the horizontal stretch factor, only x values are affected. Super important. So let's look on our graph. Every 2 units, same deal. I go 1, 2, 3, 4 units up. Every 2 units horizontally, go up 4 units vertically. So this time I'm concerned with the 2 units. And I'm going to keep the vertical unit the same. On base function, y equals square root of x, I'm going to keep the vertical translation, sorry, the vertical movement the same. So on base function y equals square root of x, every blank units horizontally go up 4 units. So let's take a look at this. So on the y value, I'm going up 4 units. What is the x value that corresponds to a y value of 4? Well, that x value, x must equal 16. So I must go 1, 2, 3, 4, 5, dot, 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 16 units total on my base function. If I do my base function here, to reach 1, 2, 1, 2, 3, 4, to reach 4 units. Okay, so it's 16 units on the base function y equals square root of x. Every 16 units horizontally go up 4 units vertically. And that you can see happens right there. Okay, so HS for horizontal stretch is so from the, I'm going from the perspective of the base function at 16. And I'm transforming. So I'm transformed from the 2 to the 16. Sorry, from the 16 to the 2. So every 2 units horizontally, I'm going 16 units vertically. Sorry, every 2 units horizontally, every 2 units horizontally on the transform function, I'm going 16 units on the 16 units horizontally on the base function. So the ratio is a 2 to 6 ratio for the horizontal component, and so the factor is 1/8. And if I make that equal to 1 over absolute value b, my b value equals 8. Here I also know, I'll put that up here, b equals -1. And for the same reason I showed you, is that my function is pointing to the left, so b is less than 0, therefore b equals -8. All right, let's put that into our equation. Y equals a square root of b times x minus h plus k. That's y equals a is 1, and b is -8 times x minus 3 minus 2. If I think about this algebraically, I'm going to use substitute point 1, 2. Y equals a times b x minus h plus k. Y is 2, a is 1. I'm solving for b. X minus 3 plus k. In this case, a small little adjustment. Oops, oh, I forgot to make some substitutions. Small little adjustment. I know it's a reflected. I know it's reflected about the y-axis, so I'm going to make that a -b, and then the x value is 1 minus 3, and then minus 2. Let's solve for b. That's 4 equals Negative b times negative 2, that's 2b. Square both sides, and I get b equals 8. So y equals negative 8 times x minus h, which is 3, minus 2. Algebraic method. Example 3. Consider the function f of x equals 1/2 times the square root of 1/16 x minus 1. Describe the transformations that were applied to y equals square root of x to obtain f. First of all, I need to factor, and I get 1/16 x minus 16. Why is this important? Because when I read this across, in general form, I have to have everything match. Remember, there are a set of brackets in the general form, so I need to factor and make a set of brackets under the radical sign. Okay? So this one, let's think about stretches. Vertical. Vertical stretch about x-axis by a factor of 1/2. Horizontal stretch about y-axis by a factor of 16. Okay, off to the side, remember, 1/16, because here I know if b equals 16, the factor is 1 over the absolute value of b, which is 1/16. So that's how I get, oops, sorry. No, sorry about that. The b value is 1/16. So the factor is 1 over the absolute value of 1 over 1/16, and that is a factor of 16. So that's how I get my factor of 16. And then the last one, man, I should have done this before. This vertical stretch, that's a value of 1/2. And then horizontal translation. So horizontal translation, 16 units to the right, because h equals 16. Okay, letter B. State the equation of a function in the form g of x equals a times x minus h, which is equivalent to our original function here. Okay, so this time it looks like we just want only a vertical stretch. So how do we eliminate that horizontal stretch? So we're writing equivalent functions. So I just need to do some algebraic manipulation here. So I start with that, and then I can see that the square root of 1/16 is 1/4, and I'm left with x minus 16 as the radicand. So my other way to write this is 1/8 times the square root of x minus 16. So all of this is a vertical stretch about x-axis by a factor of 1/8, and still a horizontal translation 16 units to the right. Let's look at it a different way. State the equation of a function in the form h of x equals b times x minus h, which is equivalent to the original function. Now, I only want a horizontal stretch. So let's use our skills and knowledge of manipulating radicals. I need to make this mixed radical an entire radical. First, let's start off with this, 1/2. I'm going to factor. So I have x minus 16. So I have 1/2 times the square root of 1/16 times x minus 16. And when I convert that 1/2 as part of the radicand, it turns into 1/4. And now I have what times 1/16 times x minus 16. So f of x equals square root of 1/64 times x minus 16. So now my b value equals 1/64. So horizontal stretch. So the factor is 1 over absolute value of 1/64. 1 over the absolute value of 1/64, and that is 64. So I have a horizontal stretch about the y-axis by a factor of 64. And I still have a horizontal translation 16 units to the right. Letter D, what can you conclude about the graphs and corresponding graphs equations of G and H? Well, let's say this. Equations may be written differently, but the graphs are identical. They produce the same graph, even though you're doing even though you're doing different transformations. So equations may be written differently, and I'll say in parentheses, with different transformations. Despite that, the graphs are identical. Okay. One more thing I can say is that when we're comparing vertical to horizontal stretch factors, so when we go from So this is for stretches. So when we go from horizontal to vertical, so horizontal to vertical, we go from the factor of 64. And if I take the inverse square root of it, that's the relationship. So this is an inverse square root relationship. When I go from vertical to horizontal, how does it transform? Or what is the mathematical relationship? I go from 1/8, and how do I manipulate this? I raise it to exponent -2, and that is 8 squared equals 64. So this is an inverse square, not square root, but inverse square relationship. Application example: a company estimates its cost of production using the function cost as a function of number of items. C of n equals 20 times square root of n plus 1,000, where C represents the cost in dollars to produce n items. Describe the transformations represented by this function as compared to C equal to n. So let's do this. The general form transformation model for radicals: a times square root of b times x minus h plus k. C of n equals 20 times the square root of n plus 1,000. So we line them up. A equals 20. That's a vertical stretch factor of 20. Vertical stretch about x-axis by a factor of 20. K equals 1,000. That's vertical translation. $1,000 up. H equals 0, B equals 1. And that doesn't affect the shape of the graph. Okay, graph the function using technology. What does the shape of the graph imply about the situation? So my X window, 0, 15,000, 100. Y window, 1,000, 4,000, and 100. So when I graph this, 0, 1,000, let me put a couple points in there. 3,600, 2,200, and 10,000, 3,000. What does the shape of the graph imply about the situation? So as cost C of n increases, as number of items produced n increases, cost C of n increases, but at a slower rate. And that's what this curve implies, where it curves down like that. So as we increase the number of items produced, so this is number of items. As the number of items produced increases, the cost increases, but at a slower rate because it curves down. Interpret the domain and range in this context. So the domain is n such that n is greater than or equal to 0, and n is an element of all whole numbers, right? Because we start with 0 items produced. Well, that's a whole number, and I can't produce decimal or fractional numbers. So quick note here, minimum number of items produced is 0. Number of items produced must be whole number. And that's obvious, right? No fractional numbers, no decimal numbers. Range. Cost as a function of number of items produced, that must be greater than or equal to 1,000, where cost as a function of number of items produced is an element of real numbers. Actually, let's see. Yep, real numbers, because if I have the square root of n, that gives you all kinds of like irrational numbers. So the cost can be any real number, right? Because that n value is under a radical sign. So that's why it's a real number right here, right? Because once you put a whole number in for n, and you take the square root, you're going to get an irrational number, and you could pick the whole number values of n, and you're going to get all kinds of different real numbers. And let's explain that then. When n equals 0, 0 items produced, so this is 0 items produced. If I do the math there, the minimum cost is $1,000. Cost is calculated with a radical. Therefore, cost must be classified as a real number. Okay, determine the expected cost to produce 12,000 items. And this is using your, well, let's do it algebraically. Cost as a function of 12,000 items equals 20 times 12,000, square root of 12,000, plus 1,000. And that will equal $3,190.89. Or if I trace this on my TI-84 or my Casio, for x equals 1,000, sorry, for x equals 12,000 items, the y value equals 3190.8902. So the cost to produce 12,000 items is $3,190.89.